So moving on. So this is a look at intersystems crossing, right? And so the idea here is if we have stimulated absorption as shown in the blue line, okay, we can see that intersystems crossing is really only going to be observed when we have a singlet state and a triplet state both lying in the same energy level, okay? Or not, I shouldn't say same energy level, but both have a similar energy, okay? So you can see the triplet state is slightly lower in energy than the singlet state, but all the same, they're kind of right on top of each other, okay? And particularly where the intersystems crossing is occurring, it's showing that it's occurring at these levels. In this fictitious example, intersystems crossing is occurring right there because those two upper lying vibrational levels are practically right on top of each other, okay? So there's no penalty for that transition to happen, okay? So where we see this occurring, and then of course, what's going to happen in this example, there's now an electron in this triplet state as indicated by the green arrows. All of these little arrows here are what we would call radiationless decay. So those vibrational states can relax one state at a time, right? We remember nu still has to change by plus or minus 1, but those can be occurring through what we call inelastic collisions. So collisions with neighboring molecules that impart that excess vibrational energy and cause this molecule to relax, okay? So if the radiation decay occurred from the triplet to the singlet, that would be phosphorescence, right? But if it occurred from a singlet to a singlet, for example, that would be fluorescence. And what would we would observe if we could keep track of the emission intensity of our chromophore over time, we would see the light being emitted as a result of fluorescence would decay very quickly. The phosphorescence, on the other hand, would be very slow. So as a result, I'll just say biology has really figured out how to take advantage of phosphorescence. You might have heard of these particular critters that live in caves that hardly ever see any daylight at all, okay? And so those critters that undergo bioluminescence, what that really is phosphorescence, because the phosphorescence emission intensity decays slowly. And if you were trying to biologically engineer yourself to give off light, you would really want to be undergoing phosphorescence, right? To have that nice long-lasting emission intensity. So often when you hear about bioluminescence, it's really phosphorescence that's occurring there, okay? So moving on. So here is a look at our potential energy profiles as well as what a spectrum would reveal. And I think this is really cool to see those two things side by side. So here, if we were looking at the absorption, okay, and I'll first note by pointing out this 0, 0 line right here. So what that 0, 0 line means is we're talking about nu equals 0 in the ground state. So often there's a double prime for the ground state. And nu equals 0 in the excited state. So I'll note that these are nu prime and these are nu double prime, okay? And so what that means is this peak right here, this 0, 0 peak, that actually corresponds to going from nu equals 0 here to nu equals 0 here, okay? And right, doing that vertical transition, we recognize that it will be possible, albeit it will occur with low intensity, based on this particular example that I'm showing you. And we can see that here, right? This is one of the lower intensity peaks. And so that 0, 0, right, corresponds to this peak right there. And so then if you think about it, for the emission intensity that you would observe, so notice now that there's another fluorescence peak that occurs right there, okay? And so that's from going from this, so it's not quite showing you this arrow right here, because it's actually going, again to the 0, 0 line, all the way down there. And once again, for the fluorescence, that occurs at low intensity because we recognize the wave function will look something like this, but there is a small yet finite amount of tunneling that can occur past that potential energy well that gives rise to this very low observed intensity. So now what you notice, each one of these peaks, right, corresponds to a new vibrational level within the absorption spectrum, okay? And so, for example, this very next one right here would correspond to going up from 0 to 1, so going up to that extra level, okay? So I'll say that's 0, 1. And then the next peak would correspond going to 0, 2. And as you can see on this diagram, 0, 2 definitely occurs with some nice overlap, right? So if this is level 0, 1, and 2, you can see right here definitely where it's hitting that turning point, okay? That's where it's got the best overlap. So that's where it's got the highest intensity. And so now what you can see on this diagram, it's pointing out here this A right here, which is pointing out the spacing between each one of these vibrational levels. Well, as it turns out on the absorption profile, that distance A corresponds to, I'll say, delta nu for the excited state, right? Because as each one of those goes up, that difference that you're seeing is really the difference between an excited state vibrational level, okay? And now what you're seeing right here, the peak-to-peak distance on this fluorescence profile, B, is going to give me the change in frequency, or the vibrational frequency, for the ground state, right? Because as you can tell, as each one of these goes down, we could go 0 to 0, or we could go 1 to 0, or excuse me, rather 0 to 1, or 0 to 2, etc. Okay? So in the absorption profile, you can see the vibrational energy levels for the excited state. In the fluorescence profile, you can see the vibrational energy levels of the ground state, which is pretty cool. And this, the way this works out, it's because of this fictitious example right here that has this nice Frank Condon vertical transition overlap, okay? Not all molecules have nice overlap like this. And I think I have a picture of something like that next. Yes, so just to remind you, right? When we're talking about excitation, from the ground state into all of these upper lying levels, we can see, each one of these little peaks corresponds to those vibrational energy levels. However, as soon as we're out of the well, we're just going to get nice continuous, what we call continuum absorption, which is really just related to unquantized translational motion of the photofragments, right? Because recall, once we're outside of this well, we have separate fragments right here if our molecule was AB, okay? So we can also get what's often referred to as pre-dissociation, where if, let's say, there was a repulsive state, okay? So I'll say R, so some anti-bonding state, right? We can see how excitation to one of these levels right here could then lead to, an intersystems crossing or internal conversion, depending on if the states are the like multiplicity, which could lead to then photodissociation, right, to photochemistry, okay? So that's showing you another thing that can happen to these excited states.